This discovery sounds almost unreal. A team in Gießen, Germany has isolated a molecule that stores more chemical energy than any compound confirmed so far. It carries roughly twice the energy of TNT, yet it is made only from nitrogen. For decades, many experts believed such a molecule could not be held long enough to study, because it should fall apart the moment it forms. That is why this result matters. The molecule is called hexa-nitrogen, or N6, and it forces chemistry to rethink what is possible in nitrogen chemistry today. Nitrogen in everyday air. Nitrogen is everywhere, yet it is hard to make it do anything. Life relies on nitrogen because it sits inside amino acids, proteins, and DNA. But almost all natural nitrogen is found as N2, two atoms locked together. This pair is held by a very strong triple bond. That bond makes N2 calm and unreactive, which is why the atmosphere is about 78% nitrogen gas. Single nitrogen atoms almost never appear in open air. A lone atom is so reactive that it grabs other atoms and forms new bonds immediately. The stability of N2 is useful in industry. Nitrogen can protect sensitive materials from oxygen because it does not react easily. It can also keep reactive chemicals from burning or rusting during storage. Yet the same stability is also a wall. Breaking the N2 bond takes a lot of energy, so turning air into reactive nitrogen compounds is difficult. Stable also means safe. The huge amount of nitrogen around the planet does not suddenly release energy, because N2 already sits in a low energy state. This is the deep reason why nitrogen chemistry is both powerful and stubborn. It also explains why researchers get excited when nitrogen atoms can be forced into less stable shapes. Those shapes store energy like a compressed spring, waiting to snap back into N2 the moment the barrier drops. What hexa-nitrogen is? Hexa-nitrogen is written as N6 because it contains 6 nitrogen atoms. The structure can be described as 2 N3 chains linked together. This geometry appears to give the cluster a small stability advantage over many other designs. Still, stability is a flexible word here. At room temperature, measurements suggest an average lifetime of about 35 milliseconds before it decomposes. That is roughly the time of a blink. Yet for modern spectroscopy, milliseconds can be enough. The key is that the molecule exists long enough to leave a clear signature, so its identity can be confirmed and compared with theory. Temperature changes everything. At 196 degrees C, the temperature of liquid nitrogen, N6, can remain stable for decades, with estimates extending beyond a century. Such long lifetimes are inferred from measured decay rates and the size of the energy barrier that must be crossed to fall apart. The molecule does not become magically strong. Instead, deep cold slows the motion and blocks the routes that would quickly rearrange the bonds. When N6 decomposes, it produces ordinary nitrogen gas. No carbon is involved, and there are no toxic byproducts from the molecule itself. This clean end state is part of why the result attracts attention. It suggests a class of high-energy materials that return to the same nitrogen that already fills the sky. How N6 was made and trapped. The synthesis did not begin with air. It began with silver azide, a nitrogen-rich compound known for extreme sensitivity. Silver azide can detonate from shock, friction, or heat, so the work demands strict safety practices. In the reported route, silver azide was reacted with chlorine gas, or bromine. That reaction can assemble nitrogen atoms into the larger N6 unit, but forming N6 is only half the battle. If the new molecule is allowed to move freely at normal temperature, it collapses almost immediately. To prevent that, the product was frozen at once inside an argon matrix, cooled to 196 degrees C. The timing matters because the room temperature lifetime is measured in milliseconds. Argon is chemically inert, and at this temperature it becomes a solid. The solid argon acts like a cage. It immobilizes the N6 molecules so they cannot easily rearrange into N2, and it keeps reactive neighbours away. This makes it possible to isolate tiny amounts and analyse them with state-of-the-art methods. The cooling temperature is convenient in one sense because liquid nitrogen is widely used in laboratories. Still, the need for deep cold shows how delicate the molecule remains. The achievement is therefore twofold: the chemistry that forms a neutral N6 cluster, and the physical trapping that keeps it intact long enough to measure. Decades of failed hunts. Researchers have chased these molecules for a long time, and the record was frustrating. In the 1950s, the N3 radical was detected only briefly. It could not be isolated in a stable, neutral form. Much later, in 2002, scientists detected N4, a 4-nitrogen molecule, but only during a difficult experiment, and only for a moment. The molecule was too unstable to study in detail. Larger nitrogen units did appear in other settings, but usually with extra support. Some were bonded to metals, which helped hold the nitrogen chain in place. Others existed only when they carried an electric charge. Those results were valuable, yet they did not solve the main challenge. The goal was a neutral molecule made only of nitrogen, larger than N2, that could be captured and characterized. Many experts judged that goal as nearly impossible. The reasoning was straightforward. A neutral polynitrogen chain has no stabilizing partner. It has many weak links compared with the triple bond of N2, so the chain should collapse instantly into N2. That expectation shaped the field for decades. This is why the isolation of N6 is not just one more molecule. It is a direct challenge to an old assumption about what nitrogen can and cannot do. Why longer nitrogen chains matter. Polynitrogen compounds are molecules made from more than 2 nitrogen atoms bonded only to each other. They can be imagined as chains and rings built from nitrogen alone. As the chain grows, the structure becomes more strained. That strain means stored chemical energy. If the molecule collapses, it usually ends as many N2 molecules, because N2 is the most stable state available. The fall from an unstable chain to stable N2 releases energy in one sudden step. This is why polynitrogen has been discussed as an extreme energy carrier. For scale, TNT releases about 4.2 megajoules per kilogram when it decomposes. Well-designed nitrogen chains have been predicted to exceed that by a wide margin, sometimes more than double. The idea is appealing for propulsion too. When the chain breaks, it does not just release heat, it also creates a large amount of nitrogen gas. Hot gas expands fast, which is exactly what rocket engines want. Another attractive point is cleanliness. If the only product is nitrogen gas, there is no carbon dioxide and no toxic smoke from the molecule itself. In theory, that could mean powerful energetic materials with simpler cleanup and fewer long-term pollutants. The dream is simple: high energy, simple products, and no carbon chemistry. The reality, however, has always been the same problem. The molecules tend to vanish as soon as they form. Promise, problems, and next steps. The energy number is what grabs headlines. When N6 decomposes, it releases about 9.2 megajoules per kilogram. That is more than twice the energy released by TNT and higher than HMX, one of the most powerful common high explosives. In principle, a material that releases that much energy while producing only nitrogen gas could be valuable for propulsion. A rapid burst of energy plus a surge of expanding gas is the basic recipe for thrust. The study leaders have even suggested it would not burn like a normal flame, but would deliver a sharp pulse of energy and gas, which is attractive for rocket engines. Because the product is nitrogen, it would be non-toxic and non-corrosive compared with many energetic chemicals. The same behavior could also make it an unusually clean explosive in terms of reaction products. But major hurdles remain. First is stability. A lifetime of 35 milliseconds at room temperature is far too short for storage, transport, or routine handling. Second is scale. So far, only tiny quantities have been produced, and the methods are complex and hard to scale, especially with dangerous precursors. Third is control. N6 releases energy as a sudden burst. That is useful for detonation, but a fuel or energy store needs a controlled, steady release. No clear technology yet shows how to tame that burst safely. There are also concerns about misuse, because any ultra-energetic compound invites military interest. Even so, the scientific value is clear. Chemist Carl Christie has called the work spectacular, and comments in the field have suggested it is Nobel level in significance. The researchers have even argued that larger clusters, such as N10, may now be within reach. Whether or not those goals are met, N6 already serves as proof that neutral, pure polynitrogen can be captured and studied. Hexa-nitrogen is not a ready-made fuel, and it is not an off-the-shelf explosive. Its value today is deeper. It shows that chemistry can trap a neutral nitrogen cluster that once seemed impossible to hold. That single step opens a path toward larger nitrogen chains and new strategies for stabilization. Future work will test safer routes, better trapping methods, and ways to control how energy is released. If those pieces ever come together, the payoff could be huge. For now, N6 stands as a rare kind of breakthrough, a tiny, fragile molecule that still reshapes big scientific expectations in years ahead.